So today we will quickly review the section 2.3 and talk about the squeeze theorem here. It will be very fast, no rush. But before we go to the squeeze theorem, let us review some of the previous examples. So we applied the laws to find the limit, right? In the first example here, we were able to, if we can substitute this value to the limit here, and it is defined, then we're good, okay? Sometimes it's not the case. We have to apply some perfect square rules to deal with the second example, for example, right? And in the third case here, we may have to deal with square root. And here are some example useful formula we have to use. It is very useful. You can find it in Moodle's in references. You see a table of formulas. So a plus b squared. So what is it? Perfect. And thank you, Elijah. Good job. Perfect. For example, now if we have x plus 2 squared, can we apply the previous example formula here? It will be
x squared.
4x, right?
Yes, 2x and then times the second parameter, which is 2 in this case. Very good, you're doing fast. 2 squared, or then we can simplify it. It will be x squared plus 4x plus 4. That's very useful, right? Good job. And the similar things, if we have a minus b squared, it will be
Minus 2ab.
Very good. Perfect. So we're mathematicians and we're lazy. We will somehow do the similar things. If we apply, here is a negative sign, then we can write it here, right? A negative sign here, right? Implying also we're lazy, we can write it this way. X minus 2 squared becomes x squared minus 4x plus 4. Same things, okay? It's very useful. Remember these. And another formula, a squared minus b squared. It will be? Thank you. Good job. What is your name? I'm sorry. Emma. Thank you, Emma. Okay. Is it clear for everyone? Good. Now, I'm going to show you a very useful trick. Okay. Now, can you help me with this? X minus 2 times x plus 3. So, use your draft paper and try to explain this using distribution rule. Tell me your result. Okay, everyone take a piece of paper, try to do it. Okay.
X squared plus x minus 6.
Very good. Can we just do it slowly? Start from, okay, distribution rule, right?
Yeah.
So we will,
The first x.
Two.
Print the pattern.
Yes, and then distribute this guy to the second one here, right? Perfect. It will be?
X squared.
Yes, x times x equal to x squared and?
3x.
Very good. And then we distribute the second guy here, right? To this guy, and the same thing. Okay, then it will be?
Negative
Yes, be careful. Here is a negative sign. It should be -2 times x. Or you can think of this way. Plus -2 times x, right? Be careful with the negative sign. It's very dangerous. Okay. And then,
-6.
yes, plus -6. Or it is -2 times 3. So let us simplify it here. It will be
X squared plus x.
very good. But let me write it this way. It would be 3
3,
and
2,
subtract 2 here, right? Good job. And the last one, it will be
-6.
6. Yes, -6, or I just write 2 times 3 here. Okay. Now we simplify it. It will be
X squared plus x.
good job. -6. So now imagine in your head, if we do in the reverse case, you're given that x squared plus x minus 6. So how can we group it and give us the origin and the product here, right? The interesting things here is that, observe this guy. This guy is a product of 2 and 3. And here, this guy, or you can write the product of 3 times -2 here, right? And in the middle guy here, it is the sum of these two numbers. Okay. So now, in general, if we multiply x plus a is any number, abstract things here, x plus b. If we distribute, what do we have here? And we know that it should be a plus b x and then plus a times b, right? So in the future, if you see something, so now keep in mind that we can manipulate this guy, right? This is a number, and we write it in terms of a product of two numbers. And somehow if we see this sum here, we will manipulate it and try to get this product. Now, go back to the example before. Here. Let me see, sorry. Where was it? The previous one, we did compute the limit of well, don't worry for now. We'll do it in the next example. But for now, just a reminder. Okay. And today, we'll talk about the squeeze theorem. It says that if the function f is smaller than the function g, here, near a, where a is a number, right? Then the limit of f smaller than the limit of g. Makes sense, right? A bigger one has a limit will be bigger than the smaller one here. And if we're given the function f and the function h here, satisfying that fx is smaller than gx, smaller than h of x here, then the limit of the two sides, if the limit of the two sides are the same, which is equal to L here, then the limit of the middle one should be the same values as that guy. Okay, squeeze theorem, or sometimes we call it sandwich theorem. Make us hungry, right? Okay, now let us apply it to this example and see how we can do it. So example, we compute the limit of x squared times sine of 1 over x when x approaches 0. We need to show that this limit is equal to 0. Now, try to think about a solution yourself. We'll discuss a little later. Can you see it? Okay, good. People on Zoom, can you follow? Thank you. Good job. Okay. Before we do this example and the hint, we should use the squeeze theorem here, right? Suppose this is the function g. Then we need to find the function f and h somehow. Yeah, it's larger or bigger, smaller or bigger than this function. What do you think about this guy? What is special things about this? What is the difficulty of this function? It's sine and it's hard, right? And so, and at x is equal to 0, what is sine of 1 over x here? Very good. It's undefined at 0. So we have to somehow get rid of this guy, right? Anything else about the function sine here? What is the range of this function? It is true, but can we find a better estimation?
-41.
Yes, thank you. This is a better estimation, right? So let us write it down because we know that sine is always larger than -1 and smaller than 1. Okay. Sorry, what is your name again?
Isaac.
Isaac. Thank you, Isaac. So, interesting. It is bounded by -1 and 1. So, how about x squared? What is special about x squared? Always positive. Perfect. Now, remember, if we multiply it in the inequality, if we multiply things with positive number, it resolves that inequality, right? So how about if we multiply x squared to this inequality? X squared, if we multiply it with sine over 1 over x, right? We multiply it for those. Is it true? Okay. Don't be confused. Okay, let us break it down. I'm sorry. So the two sign inequality here is we can break it this way. So the first inequality, it will be -1 times x squared smaller than x squared times sine 1 over x. And the second inequality will be x squared times sine 1 over x here smaller than 1 times x squared. They're combined, we're lazy, right? We try to write it this way. Simply, this one is the same as this guy and this guy, okay? Are you comfortable now? Yes, very good. Now, interesting. We see that the sandwich is right here. If we take the limit, imagine here, look at this here. Something smaller than something else, smaller than another one. And we take the limit of the two sides, right? So now consider the limit of the left when x approaches 0. The left side here, it is -1 times x squared, or we can write it as -x squared, right? What is it? Yeah. We can substitute the value here, right? It will be -0 squared or 0. Very good. Thank you, Jane, everyone. How about the right term of the sandwich? Limit when x approaches 0 of x squared? Also 0. So the left and the right, we take the limit. They're both 0. So in the middle, what can we say? Yes. So we can simply copy it this way. So remember, if we take the limit, right? And we see that it is 0 smaller than the limit of x to 0 of x squared sine of 1 over x smaller than 0. Therefore, we have what we need to show, right? So we have to use it because this guy is undefined at x is equal to 0, okay? By the squeeze theorem. Yes.
So we do another one, or do you just multiply by x squared?
I'm sorry.
You just multiply the
Yes, we first multiply x squared at both sides, right? Everything. And x squared is a positive number. It does not change the inequality. But if we multiply with a negative number, should be careful. Okay? For example, but now we are done with this. Now, just be careful. If we see that sine of 1 over x smaller than 1, then larger than -1, if we multiply it here with, so x squared is positive, then -x squared will be negative, right? So on the right side here, it will be 1 times -x squared. The left side, 1 times -x squared. We multiply -x squared everywhere here. So what is the inequality here? Yes. Then Greater, yes, be careful. We multiply with a negative number. We should change the sign of inequality. Good job. Okay. Be careful when we deal with a negative number and inequality. Are we good? Yes. So the limit here, we try to apply the squeeze theorem to find this guy. Yes, we need to show it here, right? The question is, we need to show it. We don't know what it is at x is equal to 0 because it is undefined at x is equal to 0, right? Sign of something is not defined, we don't know. So we need to find a way to get rid of this sign. So we think about the squeeze theorem because sign is bounded by -1 and 1 here. We take advantage of this properties.
Wait, so if the original problem had said limit x goes to 0 of x squared, and then like if it equals like 2, would you do 1 on the left side and then like 3 on the right side instead? Because that's in the middle.
If we're computing when the limit approaches 2, then we can substitute directly to here because sine at 1/2 will be a specific number. We don't have any difficulty.
I think she's asking about the like -1. She's confused why it's -1.
Okay. So let us go back to the definition of sine and cosine. Okay. Trigonometry. So sine and cosine are the definition of this guy. In trigonometry, if we have a right angle here and the triangle A, B, C, this is A, this is B, and this is C, the leg here. Then definition, sine of, let's say, the angle B, definition. So it will be, what is it?
Lowercase b over lowercase a.
Yes, B over A. And cosine of B will be
C over b.
cosine,
No, it's C over
C over A. So in the right angle, the hypotenuse is the longest leg, right? So it is longest. Then A is always larger or equal to B and C, right? So therefore, this number is always because B is always small. Yes, it's always less than 1. Thank you, Madison. Perfect. It's always less than 1.
or equal to, oh wait, never mind, there's definitely.
And cosine is always smaller than 1, right? That is why cosine and sine are always smaller than 1.
Is it less than or equal to or less?
Less than or equal. Because sometimes the angle here, suppose the angle is 0, then it will be simply a line here, right? And A over A will be in that special case. A over A give us 1.
That's why the standard sine and cosine curves stop at -1.
Yes, that is why it's always smaller than 1. But then they generalize it and consider the negative angle. And in that case, we see that, okay, it is larger than -1, cannot exceed that. Okay, very good. And if you don't remember, so we can talk about it right now. So here, the unit circle. It is a very important concept here. The unit circle. imagine there's a coordinate in the x and the y direction. From definition, okay, suppose the axis here is the value. Right here at this point, this is 0, up to this point is 1, and here it cut this axis at 1 as well, and here is -1, here is -1. So because we know that sine and cosine are always larger or equal to larger than -1 and smaller than 1, we use this unit circle to describe the trigonometry things. And we define that, okay, this axis, we call it the sine axis and the cosine axis here. And here is the sine axis. Let's say the angle alpha. And the definition, we can show it this way. Okay, if we are given the angle alpha here, suppose it's not very special, should be right here is better. Suppose this is alpha, the angle, and definition, the angle in radians, the angle alpha start at this point is at 0, it goes counterclockwise. Okay, that is the positive direction. Just definition, we have to admit. Convention. In the opposite direction, it is the negative direction. Okay. Now, suppose, and the unit circle here, what is the length of this guy from 0 to this? Let us define the point P here. Okay, what is the distance from 0 to P here? What is it? Pi over 3. We don't know yet because we don't know what alpha is, right? But the distance from 0 to P, P is on the circle. What is the radius of the circle? 1, right? 1 here, right? If we project P to the OX axis and we call it the point A right here. Okay, so inside the triangle OAP, okay, what is cosine of alpha? Cosine will be the opposite legs divided by the hypotenuse. Oh, yeah, adjacent, my bad, adjacent. It will be OA, right? Distance here, right? When we project, this will be a right angle, okay? And what is it? OA over OP, right? And what is OP? Yes, it's simply the distance from O to A. Oh, okay. Now we got it. So we see that the distance from O to A here will be exactly the value of cosine alpha, right? It's very convenient when we use a unit circle. How about sine of alpha? I hear some sounds and it seems to be very good. So if I define the projection right here, right? The point here is B, the projection of B to this y-axis. Then what is sine of alpha? AP. Very good. AP divided by OP, right? And but AP, because this is a rectangle, right? AP, can we write it as OB? They're the same thing, right? Let us write it this way. And OP is 1, right? And finally, it will be OB. Or in order to find the sine alpha, we just project to the y-axis, and this distance will be exactly the value of sine alpha, right? Very easy to remember. So is it clear now? Okay. Yes.
I don't understand why it would just be AP over 1.
AP over 1?
Yeah. Like, wouldn't that be the same thing?
Yeah, I was saying.
He's just moving it to the other side.
AP is the same as OB because it is a rectangle. So we want to take advantage of that. Yeah. It's still, yes, you're right, completely right. It is AP, but we want to see that values on the y-axis, right? That is why we just replace that by OB. It's easier to see.
Wait, so OA and OP are the same length?
No, they're not necessarily to be the same. It depends on the angle. So in this case, the angle alpha is this at this position, right? Then we have OP is this much and OB is a little shorter, right? But now, let us play another game. Okay, trick here. So for now, is it clear for sine and cosine of this angle? Okay, yeah, right. Move on. Now, I give you this alpha. The alpha here, let us remove these confusing things. Oops. Now, oops. So now, if I give this angle, again, in radians, the angle alpha will start from this position, right? It run up to this point, and we call it the beta. Okay. Now we have a new angle, which is between. Okay. I'm sorry. Let us define the value of the angle. It is 0 at this point, and what is it here on top of this? 90 degree, or yes. Thank you. Perfect. And right here. Very good. And here? Yeah, just continue this way, right? This is when we go in the positive direction. Okay? How about we go in the negative direction? If we go in the negative direction, it will be, yes. Good job. And here? Very good. And here? Yeah. So the value of the angle are different, but when we show it on the unit circle here, they may be at the same point. Okay. Now, suppose we are given the angle beta is larger than pi over 2 and smaller than pi, right? What is the cosine of that beta? In order to find the cosine, we will project to the cosine axis, right? The cosine axis is this line here, right? Then it will be this, okay? On the cosine axis, the distance from the projected point here to the origin will be the cosine of this. You see it now? Okay. Oops. Is it positive or negative? Negative. Why? Thank you. Perfect. Exactly. Or you see that here on this axis is on the left side of 0, right? It's negative. So if someone asks you, okay, if we're given the angle from larger than pi over 2, smaller than pi, would the cosine of that angle would be positive or negative? Then you can visualize in your head, right? Your unit circle, and okay, we see it is in the second quadrant, project to the cosine axis, it is a negative number. So cosine of this angle will be a negative one. Okay. How about the sine? Yes, very good. Sine of this angle right here, we project to the sine axis here. And again, this distance tells us about the sine of beta. Okay, good job. Is there any question up to this point? This? Okay, good question. So any quarter here, we define that 180 degree will be pi. And here is the half of the circle, 1/4. So we define it, okay, what the distance from this point to this will be pi over 2. If we go in the positive direction, we just add pi over 2 and continue this way. Or if we go in the negative direction, we just subtract pi over 2. Just convention, okay? Any other question? So we are a little behind our schedule, right? But it's fine. We are reviewing very good stuff here. Very important. In the future, just remember this unit circle. It will recover all the things about trigonometry. How about now let us do a quick question here. If we're given the angle alpha will be in the third quadrant. Suppose the angle alpha will be this big from here to here. Let us call it the angle gamma here. The cosine of gamma, is it positive or negative?
Negative.
Good job. Sine of the angle gamma here? Negative, because we projected here is negative as well. It's easy, right? Piece of cake for you now. Now, yeah, let us take this chance to explain tangent and cotangent at the same time. Okay, let us draw another unit circle and we'll talk about tangent and cotangent. It's very useful. Okay, now if we're given the unit circle here, and cosine axis is this guy, and the same story. This is sine axis. This is 0, this is 1, the value and the angle here. Then now, if we're given the angle alpha, we know how to find sine and cosine by projecting these two guys to the sine and cosine axis, right? The question is, what is the tangent of alpha? If this is the point P, this is A, this is B. What is tan alpha in this case?
AP over OA.
Good job, over OA. Right? Or we can write, because AP is the same as OB, right?
Yeah.
And OA here or OB, we know that it is sine alpha, right? What is OA? Great. Good job. Now, look at this line. If we draw a line that is parallel to the axis AP, okay, imagine this line will continue going straight this way. Okay, and it cut here at the point, let us call M, right? So now, we're not done yet. Please pay attention here. Look at this triangle. Let us call the point here is K. K is this point right here. Consider the triangle OPA and the triangle OMK. How are they? Great. Thank you, Jane and Isaac. I'm sorry. What is your name? I'm sorry. Christian. Thank you, Christian. They're similar, right? Good job. Then the triangle OAP is similar to the triangle OKM. Therefore, we have the ratio. The leg here divided by this leg, right? It means AP divided by MK is the same as what?
OB divided by OM.
Beautiful. Thank you. Great. And OP, what is it? Just one, right? Okay. So we see that all the tangent here how can we say that? So here you see that the tangent here at this point, it will be this distance, right? OM, let me see. Sorry. Let us use a different ratio here. If we use the ratio AP over, sorry, it should be like this. AP divided by OA will be the same as MK divided by OK. And then OK is 1. Then we see that this distance will tell us the tangent alpha from K to M here. And this is the axis of tan alpha. Okay, go home and play with this. Thank you so much. Dismiss here. I'll see you tomorrow.